Okay, section 7 of lesson 1, we are going to talk about RNS or residue number systems. So what is RNS? RNS is a way to represent numbers such that this representation allows us to do what we call carryless addition and multiplication. Now, a residue number system actually cannot represent any type of algebraic structure, and specifically represents just modular rings that obey the following. So we define big M, as you can see here, right? And big M is really just a product of MIs. Okay, let's say M1 to M small n. And the important thing is that these MIs have to be co-prime, okay, or pairwise co-prime. Now, when we represent a number, so we actually big M, we would represent everything modulo big M. Okay, and the RNS representation would actually be as follows. So if I take AI, right, or I see that it's already written here, right? So AI really is just the standard integer representation modulo mi. Okay, so I have all these, we can call them right, these sort of like partial remainders. Now, if I take this representation and then I want to add in this representation, it's very easy. I add individually per, maybe we can call it coordinates. Okay, so the output of A plus B in RNS representation is C, such that CI is simply the sum of AI and BI modulo MI. And multiplication is exactly the same. Okay, we're not going to really prove this, but you'll get a sense for it a bit later. Now, we've already said that ZM is an integer ring. It's not a field, right? Because the M is actually the composite of a few primes. And as such, it has what's called zero divisors. Which means that there exist two numbers within ZM, right? Such that their product is 0 modulo M. And this is actually often a bit inconvenient, okay? And such that A nor B are 0, okay? This is actually somewhat inconvenient many times, but the advantage of this representation still makes this rather useful, even with the zero divisors. Okay, it is possible to represent, to use RNS to represent numbers within another ring or perhaps even a field. ZL, such that L is less than M, and you can do this with RNS, but you would need to add a little bit more to this basic representation, right? So it's no longer going to be just A1 to AN. It will have maybe like another residue added to it, or another few residues that will show you when you've actually overflown L and you need to wrap around. Okay. So Chinese remainder theorem. So Chinese remainder theorem is really just a way to go back from the RNS representation to the standard integer representation. Let's show how it works, and I think it will be pretty self-explanatory. Okay, so we compute these MIs, okay, big MIs. And the big MI is basically if M is the product of all MIs, okay, then big MI is actually the product of all MIs or all MJs except for MIs. So another way to write it would be as in the product, I not equal, or actually, yeah, this will be confusing. We'll do it like this. J not equal I MJs, okay? You take all the MJs and you drop out MI. Now, if we use these MIs and then we have, right, like if we look at say, A1 is multiplied by this constant whose M1 to the power minus 1 mod small m1, and that times big M1, and then A2 is exactly, we multiplied by the corresponding constant, but this time the one for small m2. Why is this good? Well, imagine we want to compute this, right? So A tag is like the sum of all of these partial products, okay? Where A1, A2, and so forth are actually those numbers in the RNS representation. Why is this good? Well, let's actually show. We claim that A tag mod MI is actually equal to AI. Okay, which would show you that actually A tag or that the AIs are actually a representative of some number A tag. Okay, let's just take an example. Let's just take for example a tag mod maybe M3. Okay, so now for that, let's just say that it's a lot of things. Plus, let's just take two of them that are maybe relevant for us. So we'll take A2 times M2 minus 1 mod M2, right? And then we'll take A3 M3 minus 1 mod. Excuse me, I actually made a mistake here. Okay, so this is mod small m2, and this is times m2, and this is mod small m3 times m3. Okay, so let's see what happens when I take mod 3 of this. Okay, so if I take mod 3 of this part, okay, right, maybe if we'll go to red, it's going to be better. Okay, so this guy, we'll take mod 3 of this one, and then we'll take mod 3 in green, mod, excuse me, small m3, of course. This guy. Okay. So if I look at the red one, well, since M2, right, M2 is actually, if I write it out, right, M2 will be equal to M3 times the product of whatever, like a few other things. So when we do modulo of M2, right, so mod M3 of this is equal 0. Okay, because it's basically just a multiple of M3. So this guy, the red guy, goes to 0. Okay. Now, let's see what happens when we do the same thing, but for the green guy, right? The green guy actually has like it is with regards to M3. So M3, big M3 doesn't have small m3 in it. If we rewrite this slightly, right, it'd be M3, and then we would have M3 to the minus 1 mod M3, and take this one multiplied by big M3 mod M3. So from just right, modular rules, we can actually erase this one, right? Because we got the modulo 3 on the whole thing. Then if we do that, right, then actually M3 to the minus 1 cancels out with M3. They just equal 1, right? And then what I finally have is A3 mod M3, but that's just equal to A3 because A3 was already modulo M3. So this guy goes to A3, okay? So basically, A tag, if we think about it, A tag really is a number that that its RNS form is actually A1, A2, AN. Okay. Okay, so using CRT, right, we've shown already that we need these factors. Since we know all m's a priori, we can actually pre-compute these. We call it mu I. And then CRT is simply the sum of these products. And then finally, we need to take modulo big M because we will typically not be in the canonical form of modulo M. Okay, maybe just a small comment about representing signed numbers using RNS. So sometimes we want to represent signed numbers rather than unsigned, right? So instead of representing the number 0 to m minus 1, I actually want to represent something like minus m divided by 2, and then all the way usually to m divided by 2 minus 1, right? That would be like the 2's complement representation, okay? Actually, here, since we're not talking specifically about bits, we probably can often even just represent anything from minus or not. You know what? Let's just keep it like that. We'll just forget about these small technicalities now. How do we do that? Okay, so one way to do it, option 1, maybe the simplest one, is to add a bias before converting to RNS, do everything in RNS, and then convert back. Another option would be to keep track of the sign. Where would that matter? Well, for addition and scalar multiplication, that makes no difference, right? Because we're within just a group structure, then we don't have a problem actually representing things in different regions. But when we go to multiplication, because it's not a field, that gets a bit trickier, and then we need to remember what the sign of the number was. If we do know the sign, then there is an easy way to negate an RNS, and that is just by subtracting from each coordinate its MI. Okay, so let's do just a small RNS exercise. Really just practicing, like representing and then going back, like going in and out of RNS representation. So this is our prime number up here. 9177, and it's made up of a product of M1, M2, M3, small m's. Okay, so what we used, this is really like what we used for maybe big M previously. Okay, just to be consistent with our previous terminology. So the first thing that I'll do is maybe I'll represent A and B in RNS. So that's pretty easy. I take like A, which is 5832, and I mod it by 19. Okay. So I'm not going to actually compute it here. I'll just give you the results. So it's 18, 15, and 13. And then B, similarly, is 8, 12, 16. And then A times B, right? C, which is equal to A times B. This you could compute yourself. It would be like 18 times 8 modulo 19, and so on. Turns out to be 11, 12, 1. You can already see why this representation is actually it's very easy to work in RNS. But now how do we go back from this representation of the product to the standard integer representation? Well, for that, we need to compute the m's, right? And then the mu's. So M1, okay. M1 is the product of small m2 and small m3. And again, I'm not going to go through all the computation. I'll just give you the final answers. Big M2 is 437, and big M3 is 399. Now, if I go from that to mu1, mu2, and mu3, and you can look at the definition. We did it before a few times. It's just going to be 12, 5, and 3. I'll remind you that this whole red block is pre-computed, so there's no need to do any of this in real time. And then CRT, right? So this is the CRT maybe for C. Okay. We take, again, C is 11, 12, and 1. Okay. So what we do is we take the first coordinate, 11 times mu1, which is 12, times m1, which is 483, okay, plus 12 times mu2, which is 5, times m2, which is 437, plus 1 times mu3, which is 3, times m3, big M3, which is 399, and you'll have to believe me that this turns out to be 91173, which if I then go and check, I'll see that 91173 minus 9 times P is actually 8580. And if you actually check this directly, right, this should be equal to A times B mod P. And we're done.